Okay, so 5G networks are beginning to appear now. So basically, most of it is on the radio part, so it doesn't really concern what we cover here. But there's this all new array of applications that come from the new radio capabilities, but also from marketing requirements and a set of emerging technologies that pose a lot of new requirements on the network. So in these new networks, we have to have big increases in data rates and low latency, and this is what's taken care of when we are talking about the radio part. So basically, the big increase in data rate and low latency on the radio part, because on the core we already have fiber networks and all that. Also, energy efficiency is also becoming a concern. And then we have some things that traditional networks have very deep difficulty in providing. Specifically, this context-aware networking, quality of experience-aware billing and pricing, quality of experience and user experience, and high availability, security and mobility. So, especially here, we have use cases now that aren't still available, but that 5G networks should support, like sub-millisecond latencies together with high availability in the order of 99.999%. So this poses a lot of challenges, and in terms of requirements, and also we have a kind of convergence starting to appear between computing, the cloud, and the communication systems, the network. So a 5G network is a system where these two things are intertwined, so they are combined. So the idea is that in these networks, we have almost like, the network is almost like what happened in cloud computing was that we started having hardware being used or being separated by the computing that uses them. Okay, so we virtualized computers using containers and virtual machines, right? Now in the networks, we are following the same path. We have the physical hardware, the routers, the switches, okay? And we are going to virtualize them, okay? Why? Because basically, a modern network is what? It's a set of computing points that can be centralized clouds, centralized data centers, that can be fogs. Fogs is cloud near the ground, meaning that data centers more close to the edges of the network because of latency, and a related concept, which is mobile edge computing, which also means computing, but in this case almost in the base station, so as near to the user as possible. So basically we have three levels of computing: centralized computing in clouds, fog computing more near the aggregation nodes, and mobile edge computing at the base stations. And basically, a modern network, it doesn't do much more than interconnect these computing points. Okay, so these computing points usually also have storage. So basically, a modern network has to connect computing sites and storage sites together. That's the function. And it has to do this with several types of requirements. So the idea is that all this is virtualized. The computing, the storage, and the network. And then each time I need to build a specific service, an end-to-end service, which is a dynamic chain of services, I'm going to install this in the network, like a computer program runs on a computer. Okay, so this vision is I need to build a service, a network service, and I'm going to install it on the 5G network. So the 5G network has to be flexible, dynamic, it has to deploy services very quickly, and it has to respond to several types of services with several types of requirements. And all this has to be done automatically or programmatically. Okay, so basically, if you want to simplify, we can think of a service as a composition of generalized virtual functions that provide applications or network services. Okay, so basically nowadays, if I want to build an IoT service, I'm going to need to have application gateways that are going to be running on one of these clouds. Then I have the sensors that are connected via radio or other things to the access nodes. Okay, and then I need to deploy these application gateways on the clouds, either clouds or mobile edge computing sites or fog sites, depending on the delay requirements. And I know that this service will need a virtual machine here, a virtual machine there, and that I need to connect them, and I need to connect them in a certain order. Okay? And the network has to be able to do this. So somebody is going to give me a specification for a service, and this specification will tell me the endpoints, which computing sites I need to connect, with what delay, and with what broadband capabilities, and I need to install this on hardware. I need to create this service on hardware. So this means that the network will start to be seen on 3 different levels. We have the infrastructure level. Okay, this is what we have been seeing so far, up to the SDN. We were configuring this part here, the hardware infrastructure. These are the devices, the routers, the switches, the firewalls. Okay, and if we add the computing and the storage, the servers and the disks. Okay, and the access technologies, the radio antennas, the fiber cables, all that. So the physical network is the infrastructure. Okay, this physical network connects these pyramid sites here, which are clouds or data centers. You see here, some more close to the edge, some more central. And this is the representation, this square here is representing one of these pyramids, okay? So each one of these pyramids is a network like this that has a bunch of switches and a bunch of servers, okay? So each of these sites is a data center network. We have huge data centers like Google and Facebook, which are central data centers, or public clouds like AWS from Amazon, or Microsoft Azure, Google Cloud Computing Platform, Cloud Platform, all those things that are heavily used, for example, by companies that use them for their everyday work. And then we have for things like the smart grid or smart cities, IoT applications, things that are delay sensitive, where instead of using those big cloud data centers, I have smaller data centers where the applications are running, the application servers are running. And when I build a service, I need to interconnect all these things. I need to know where I'm going to deploy my VMs, my containers, and how am I going to connect the several data centers that are involved. So for this, I need a second layer, a layer of virtualization. Okay? So this layer of virtualization virtualizes the infrastructure. Okay? So this has, for example, network functions that are run as software and are running on these data centers. These have functions, SDN controllers, for example, that control the network. So I have to have a means here in this second layer to build a virtual overlay network on top of my infrastructure. And then I have the service layer, which is the service itself that is using this virtualized overlay running on the hardware. So we're simple. In order to make this more concrete, we have this figure here, okay, with a more concrete example. You see, for example, here you have an infrastructure with some switches, okay, some radio access, a radio access network that is connecting, for example, an IoT service, an autonomous vehicle service, and the regular smartphone enhanced mobile broadband service. And each of these things has its own requirements, and it has to connect to its own clouds, okay? So, for example, the autonomous car slice might need to connect to a mobile edge cloud. The smartphone slice probably needs to connect to a network cloud or a more central cloud, and so on. And so what I have here is that I need to virtualize this infrastructure. So I have communication infrastructure, I have computing infrastructure inside these clouds, and then I have the internet if I want to connect this also to outside of this service that I'm building. So in order to build these three services, I'm going to have to run things here, and I'm going to have to run things here, and I have to connect the things that are running in each of the sites together, and sometimes in a specific order. For example, I might be running a firewall here for the smartphone slice, and I need the traffic to come from the radio network to this data center, go through the firewall, and then, for example, go through a load balancer that goes to a video site, because one of the things that this slice gives to smartphones is IPTV, for example. Okay, and I have to build a service here. So I need to virtualize this somehow. And this is where the SDN technology enters here. Okay, so I need to control this via software so that I can build this abstraction layer that controls the network and shows me a network interconnecting virtual machines, basically. So I will create virtual machines in the clouds or containers, and then I'm going to create tunnels or whatever to connect them, building a virtual network. Okay, and this all works with APIs. For example, one API that we saw that can be used here is OpenFlow, but we can have others. Okay, and then from this virtualization layer up, I need also APIs so that I can easily create, with an orchestration level, services across the network, from the radio network to the access network to the transport network to the internet. Because to build a service, I might need to have things on all this. So the service might need to access the internet, so I have to have connectivity to the internet. The service might need to access some specific servers that are on these clouds, so I need to connect them to these clouds, and I might need to connect all this in a specific order. Okay? So you see here, in this case, we have the RAN, the radio area network, then we have a transport network and a core network. And in all of these, I have this problem of virtualizing resources, okay, divide them between services, and then configure all this automatically. So these services have brought the idea of something that is called a network slice. So what will happen is that I have the infrastructure is virtualized on a number of different slices. It's like if I'm building virtual networks on top of the real network, And each of these virtual networks is what we call the network slice, so a slice of the network. Okay, so these are self-contained networks that can be orchestrated in different ways and have different requirements. So there are some specific types of slices that are very discussed. For example, enhanced broadband mobile slices, which are slices that need a lot they need a broadband, they need high bit transfer rates, but for example don't need high reliability and don't need low delays. Okay, we are talking, these slices are used, for example, for smartphones, for going to YouTube, for using Facebook, for all of these applications that are not very delay sensitive, but are broadband hungry. And then we'll have slices that need very low delays and need to be ultra reliable. For example, for tactile applications, remote surgery, even for autonomous vehicles, delay is also sensitive because we need to assure that cars communicate with low delay. And then we have also the slices for Internet of Things. In this case, it's not a question of delay sometimes, nor broadband, because the communications are very small, but they have requirements of a large number of devices. So when we are talking on Internet of Things, these are slices that can have to deal with hundreds of thousands of hosts. And this is the problem in these slices. So we have slices where the problem is broadband, we have slices where the problem is having low delay, we have slices where the problem is dealing with a huge number of hosts. And each of them has to be built and orchestrated in a certain way. But you see, the network is always the same thing. Computing sites, which are the red things here, access points, radio or not, and then a network that needs to transport these things between the users, and the computing sites. So building a slice has a lot of challenges. So in order to achieve this, we need to be able to manage physical and virtualized resources on a seamless way, in flexible way. Okay, we need to have end-to-end service orchestration that needs to be agile, that needs to be quick, and it has to deal with the radio network, the access network, the core network, and it has to separate all the slices, and I need to enable end-to-end connectivity in a programmable way. So all these challenges, in order to be met, we can't have traditional networks, as we saw in the first part of the class. So I can't do any of this by going into a CLI and configure manually switches and routers. I can't build such a flexible network and such an automatized network in that way. So SDN is the key technology to achieve this in any of the flavors that we saw. When we say here SDN, it does not mean open flow. It can be SDN with an API. It can be SDN that is automatically configuring devices with netconf. So it can be a network that still is quite close to what we studied. It still can have a control plane. It still can have its forwarding protocols, its routing protocols running in the devices, but it has to be at least manageable via software. Okay, this is what SDN means here. We need to at least be able to do this via software in order to have the desired flexibility and the capability to virtualize the hardware infrastructure. Another key technology is what we call network function virtualization. which is sometimes mixed with SDN, but are two different concepts that are that will be used together, or that are meant to be used together. Okay, so SDN basically provides programmable connectivity. Okay, so this means that using SDN I can have dynamic steering of traffic. So I can easily build a service and instruct the switches and the routers how the traffic should go. Okay, either using OpenFlow, either using netconf and configuring routing in the way that I want, or whatever. Okay, NFV is to create virtualized services. Okay, so NFV will provide the flexibility, agility, and scalability part. What is NFV? The idea of NFV is to virtualize classic network functions, for example, routers, firewalls, deep packet inspectors, load balancers, evolved packet core nodes from mobile networks, all things that were usually specific hardware and devices, and that now can be implemented in software and be running in a computing server. And we already talked and used some of these things. You have the example of the switch that we are using in the labs, OpenV switch, which is a software implementation of a switch, or a router, because OpenV switch can also be a router. So there you have an example of a router or a switch that is implemented in software and is running in a computer, in a server. I can do the same with firewalls. I can do the same with the deep packet inspectors. I can do the same with load balancers. Okay, so this, for one thing, makes networks more cheap and more cheap to operate. Why? Because standard high-volume servers are much less expensive than dedicated hardware. Okay? So I'm going to use 10 data centers with lots of servers and a good network to interconnect them. And I'm going to build virtual networks by running virtual functions on those servers. Of course, I always need to have physical switches and routers, because those servers have to be physically connected to the other between them. Okay, so I always going to need physical routers and switches. But for example, firewalls, not so much, or deep packet inspectors or load balancers. All those special boxes do not need to exist anymore. The only ones that are always going to have to exist are switches and routers, because I'm going to need to have traffic physically being transported. But instead of having a special hardware for being a firewall, I can have this done in software in a regular server. So what happens here? If I look at this in a very high level, what I have is computing hardware, storage hardware, and network hardware, physical hardware. Okay? So these are servers, disks, and switches and routers. And I'm going to virtualize this into virtual computing, and this is a very easy concept for us nowadays. These are virtual machines or containers. Same things for virtual storage. I can have virtual disks. Usually virtual machines use virtual disks, and containers also use virtual disks. And then a virtual network. So this means that I can build here switches and routers in software that are then using real physical connections from real physical hardware, in the same way that a VM is using computing resources from a real computer or a real server. Okay? And so these virtualized network functions allow us to build the virtual network part. Okay? Then I need to have this plane here in pink that manages all this. So this has to be able, for example, to create a virtual switch and put it in real computing hardware, and then program the network hardware so that the traffic goes through the switch in the server. Okay? Or if it is a firewall, for example, to steer the traffic into the server where the firewall is. Okay, so this NFV management and orchestration has to be able to do this. It has to be able to create this virtual overlay, and for this it has to have APIs dealing with the hardware resources. Okay, so there is already a standard being proposed for this part here, for the network function virtualization management and orchestration. Okay, this is proposed by ETSI, which is a standard organization, and it's called the NFV management and orchestration, also known as MANO, NFV MANO. Okay, so what this standard proposes that we have. This is the same vision. So we have here the hardware, computing hardware, storage hardware, and network hardware. Okay, and then I have a virtualization layer. Okay, then I have a virtualization layer here, and I'm going to transform these things into a virtual network, virtual storage, and virtual computing. Okay, and this is called, these two things together, the real infrastructure and the virtualized infrastructure, is called the network function virtualization infrastructure. Okay, and then on top of this infrastructure I'm going to have virtual network functions. And then I'm going to build a service that is built of a set of these things that are connected in a given way. Okay? So a service is always something like this. It's a set of virtualized network functions, which are VMs or containers that need to be deployed on some servers, and then I need to have a way to build a virtual network that interconnects these VMs or these containers in a specific order. So traffic has to go through this VM first, then that VM, then that container, then that container. And in order to steer the traffic in that order, I'm going to need to be able to program the network hardware. Okay? So here I'm going to have VNFs, and the VNFs might have some software running on top of them. I can have a virtual machine and then some software running on top of them, which is the element management system. Okay? This represents a software that is running inside a VM or a container and has a given functionality. Firewall functionality, it's an HTTP server, it's a load balancer, it's a DNS server, whatever, okay? It's a video front end, any one of these things. And then I have an operation system, that another software which it is higher level, which network operators will use, that interact with the virtualized network functions. So we need to build all this. And to build all this, I need the orchestrator. So the orchestrator will receive a description, a service and infrastructure description. So this is the description of the service that I want to use on the network. So what does this have? It has the set of VMs that are needed, how they should be connected, the order in which they should be connected, and what are the requirements. For example, it might say that I need 4 virtualized network functions, that they need to be connected in the order 4, 2, 3, 1, and that the connection for 4 to 1 must have X megabits of bandwidth, the connection from 2 to 3 must have less than X milliseconds of delay, and so on. Okay, this is what is in this service and infrastructure description. This description is fed to the network function virtualization orchestrator. Okay, what does this orchestrator do? It manages network services and starts the onboarding process of the network service descriptions. Okay, so this is where things start. It receives a description with a list of network functions, the order through which the traffic must go through them, and the requirements of bandwidth, delays, and all that. So this NFVO, Network Function Virtualization Orchestrator, will then use an interface to talk with the virtual network function manager. So this NFVO is this first part here, is this orchestrator here. This is the network function virtualization orchestrator. Okay? It receives the description, and then it uses this interface with the virtual network function manager to start the onboarding of the service. The virtual network function manager is responsible to manage the life cycle of a VNF. So what it's going to do, if you see here the interface, it's going to deploy the software on the VMs. But it needs to have the VMs already, okay? So the function of this block here is to control the softwares, okay? So it needs to receive a virtual machine or a container, and then this goes there and installs the needed software. For example, if one of the VNFs is a switch, this would, for example, could go to a virtual machine that is given and install Open vSwitch, for example, and configure Open vSwitch in a given way. But as I'm saying, this operates at VM or container level. So it needs to already have the VMs and the containers must already be created, and they must already be connected. And that is the function of the virtual infrastructure manager. Okay? So the virtualized infrastructure manager, which is this block here, will create VMs and interconnect them on the hardware, okay? Providing this layer here. How can this be done? This could be, for example, the floodlight controller with something else, because the floodlight controller only can do the steering part of the traffic. It cannot create VMs, for example. But it can be OpenStack. Okay, I can implement something like this with OpenStack, because OpenStack is a cloud orchestrator software. It can launch VMs, it can launch containers, and then use the plugin of OpenStack, for example, with OpenDaylight or ONUS, and use this to control the switches, the physical switches and routers, to connect the VMs and the containers in a specified way, to provide this virtualized network here. Okay, so the Vim does what? It manages virtual network functions at the VM or container level. So it creates the VMs and the containers and provides the connectivity. So basically, it's something that creates VMs and containers and then programs or configures the physical network hardware to steer the traffic between those VMs and those containers in the order that I need. So basically, where do SDN comes here? Okay, in this architecture. So this is the architecture for NFV orchestration. How is SDN involved? So we have the orchestrator, and this orchestrator will need to talk to an SDN controller to control the physical network resources. So if you look here at the architecture of the standard, this is the same architecture from the previous slides. What we have, for example, if I want to create, I receive a service description, and I have the orchestrator, and the orchestrator goes to the VNF managers to create the software on the VNFs, and before all that, this one, it has to tell the virtualized infrastructure to create the VMs and the containers and interconnect them. So we have SDN mainly here in the virtualized infrastructure manager, okay, because I need an SDN controller that can control the network hardware, okay, and create a virtual network, okay. So for the connection part, I need an SDN controller here. So this will create VMs, assign a given storage to them, and then it needs to use an SDN controller to connect those things. Okay? An SDN controller can be OpenFlow, it can be netconf in a more traditional network hardware. This could mean just come here and create VLANs and configure OSPF in a given way, so that the physical servers where the VMs and the containers are able to talk with each other. Another place where SDN can be is here on the top. Probably it can even be talking with this one in a higher level, okay? In this case, this is controlling, for example, virtual switches and routers that are existing here. Okay, this controller is to control physical hardware. This controller is to control virtual hardware, for example, Open vSwitch instances. So I need SDN to provide a way to establish links between VNFs and VNF components, and to support enhanced functions such as policy-based management of traffic between VNFs or dynamic bandwidth management. And then this would be this higher level SDN, okay? And then I need a lower level SDN here at the Vim layer to provide connectivities with the VNFs, okay? It's those two things that we have here. The infrastructure SDN controller provides the required connectivity with the VNFs as managed by the Vim, so it's this one below. Support the deployment and connectivity of VNFs, so support the deployment of virtual machines and containers and connectivity between them. And then we can have the tenant SDN controller that provides an overlay, okay, defining the network service on the top. Okay, so we can think of this only deals with software things. So this tenant SDN is a second layer, it's controlling virtual switches and virtual routers, while this one down here is controlling the real physical switches and hardwares, okay, to provide this abstraction, and then this one is controlling the virtual ones. They might exist or not. This one might exist or not. It depends. In a concrete example, you might have something which in none of the VMs or containers are running a virtual switcher or a virtual switch or a virtual router. Okay? In that case, you don't need this SDN controller because you don't have anything to control at the virtualized layer, because the virtualized layer is only virtualizing computing functions and storage functions or servers or whatever, or firewalls, but nothing that needs to be controlled via SDN. Then you can have a more complicated service where besides the servers and the firewalls, you also need to have virtualized switches or routers, and then these need to be controlled using this tenant. If you want to think on the example that we saw on data centers, if you remember, we can have in the data center, we can have tunnels connecting the physical switches, and then we have an overlay network which is connecting the hypervisors of each server, and you have an SDN controller that is controlling the hypervisor. That's a good example of a tenant SDN controller. If we want to translate this to this architecture, the physical network is here, okay, and then we have the hypervisors, and then we have a controller connecting the hypervisors, which is already here on the virtualized layer. And then we have another SDN controller that, for example, is creating the tunnels, the VXLAN tunnels, the gray tunnels, or the NTT tunnels. So this would be the controller that is creating the tunnels between the real networks, and then we had this one here that is mapping the hosts to the tunnels, for example. Okay, so basically SDN is very important here for the VIN in order for us to be able to control, to connect using the real hardware to connect the virtual machines or containers, and then it can be used on a higher layer to control the overlay network, because basically I'm creating an overlay network with the Vim, and I'm creating here an overlay network with the Vim, and this overlay network also needs to be configured after, and this is done using the top SDN controller. If we think on this using the slice abstraction, each slice will have its own tenant SDN controller, while all slices are controlled by this one. This is another way to distinguish the levels. If we are applying this architecture to control a 5G network where I have multiple slices, I need to create the VMs of a slice and connect them in the hardware. I need to the creation of a slice is done by this SDN controller. Okay? And this SDN controller creates several slices, okay, in a given way, and then this controller here on the top is the controller for one of the slices. You can think of this way. Problems that we have here. The first problem is, and this can be seen at the data center level, or we can put a transport network in between. In this case, I need to create a service. This service, I can call them a virtual network service chain. This virtual service network chain can be thought of as a slice, for example, because it's a service for a given use. In this case, the request is that I need network function A, network function B, network function E, network function G, and it has to be connected in this order between these 2 points, which here are users, but it could be anything, okay? So, and now I have a network where I have 4 data centers, and these links are transport networks that can connect these data centers. Okay, so here it's very simple, it's abstracted as a link, but I can also have here multiple ways to connect these two data centers. And I have another problem here, which is different, which is how do I manage this network, which is here in this link. How do I give resources of this network to all the different slices that might be going through it? Okay. So there's these two different abstract layers. I can be thinking about just my network functions. And here the problem is, in which of these data centers do I deploy VNF-A, VNF-B, VNF-E, VNF-G? Something that might happen is that some of them already exist. For example, in this scenario, in this service provider 2, there is already a network function A, a network function B, and a network function C running. And on this one, we have D and E, and here we also have E and A and F, and here we have G and C. So there are multiple ways that I could do this. I could start with A here, I can start with A here, okay? I could go from A here to B here, to E there, and then to G here. But I can also have A here, and then go to B in the same data center, and then go to E, and then go to G, okay? So there are several combinations. So this is called, this is a problem. This is NP hard if you are trying to optimize this using an optimization problem. Okay, so there is a ton of research on how to do this in an optimal way, because the standard only defines that we can do this. And I can be very naive. I can come here and do the first one that occurs, and that's it. But maybe I'm not going to be using the network in the best way. Okay, so this decision of in which of these two, for example, do I run network function A, is a problem that is called the VNF placement problem. So I can think only on the VNF placement problem, and this is just looking at the CPU and storage that is free on each of the data centers, and then, for example, choosing the one that is more free and optimize this like this. I'm only looking at the computing and storage and choosing to place on the places that are more free. Or I can mix both problems and put the network part in also. And in that case, I'm not just concerned on where I place the VNFs, I am also concerned on how I interconnect them. And in that case, it might not be the best option to put, for example, service network function A on the data center that has more available CPU, because that can have a negative impact on the network part. Okay? So this joint optimization is a very hard problem. And usually it either is defined as an optimization problem that then has to be approximated because it's NP complete, or there's a lot of research nowadays on using, for example, deep reinforcement learning and artificial intelligence to optimize this. Okay, because it does not need the model, and it will learn by observing the rewards that it gets by choosing one or other placement and one or other way to connect this. And this is only one of the problems, because then I can have another problem. Just if this link has an entire network here, so there is a cloud here. If this has a cloud here, if I have a cloud here, so it means that there are multiple switches connecting these. This goes through a network. And not only this service request, but a lot of different service requests, a lot of different slices might be traversing this cloud. And I have a different problem here, which is how do I put it? This has some topology of some networks. You know, I have some routers, whatever here. And the decision, if I put one slice here or if I put another one here, this is another problem also, okay? And there is the biggest one of them all, which is considering an end-to-end optimization in all parts. So in the placement inside the data centers, in the transport networks, and if the service has a radio part, even in the tower, okay, even in the radio access network. I can also have an optimization problem here, okay, because in the RAN I also have some things that I need to think with if I have more than one service chain using the one cell, for example. So this is again on the possible SDN positioning we already saw. So basically it's to create virtual networks. Usually I have an SDN enabled switch on the network hardware. Even if it is with netconf, I can call it an SDN enabled switch. I can have SDN applications that are running inside of virtual machines. The SDN controller itself can run on a virtual machine. Or I can have a virtual network function, for example, Open vSwitch, that itself is can be managed by SDN. Okay, so this is not fixed. There are several layers here where I can have SDN, where I can have controllers, where I can have all these things. Okay, so end to end, we have an example. In this case, each of these points can have that problem that we were seeing, the NFV placement and chaining problem. Okay, this can be a data center, you see here. So inside the data center I need to decide how this dotted red line is and where do I place the NFVs here. And then I can have a transport network in the middle. And if you look at the standard, this works in the same way. In this case, I have 3 different virtualized infrastructure managers. Okay? In this case, they called it here a one infrastructure manager, just because in this part here, I do not have virtual machines nor containers. Okay, in this part here, I'm only controlling network elements. That's why they call it here one infrastructure management instead of virtualized infrastructure management. But in the standard, it would be a VIM also. Okay, and so you have here, this is responsible to create VMs and interconnect VMs inside of this data center. This is responsible to create VMs and containers and interconnect them inside the data centers. And they deliver the traffic after the traffic goes through the VMs and the containers. They deliver it to a transport network. And then we have another virtualized infrastructure manager that is responsible to decide how the traffic goes through the transport network. All of them have to receive the specifications for the service from the orchestrator, okay? And the VNF manager, of course, must be able to create software on the virtual machines and containers of this data center, and also on the virtualized containers and machines of this data center on the right. Okay, so it has to have connectivity. This would have to have connectivity somehow. It can use the internet or some other thing, so that all these elements that are not, because this VIM is controlling some physical resources that are not in the same site as these ones. And the manager needs to be able to access both of them. Okay? So there is a lot of problems here. This is just an overview. And then there is this, we stop here and we are in the frontier here. So there aren't many deployed things of this. When we hear about 5G, the deployed 5G is on the cellular base, so it's on the radio base. This whole vision of these services, and sometimes they do a holographic interview or something, and they need to build something like this, but sometimes it is still very static. They have to go and build one of these things for the holographic interview for that specific show-off case that they are doing. Okay, so this is very, very active, and what's happening is in the industry they are building these things, and for now they are not doing this in an optimized way. So they are not just going to build this and they are going to steer it on the most obvious way, and this will result on poor utilized links, or links that will start to be congested, and they can build more services because the links are already full. When, if they did this in an optimal way, they will probably be able to create more services and more slices and all that. To do this in an optimal way is a very active research subject nowadays still. So using artificial intelligence is one of the ways. There's a ton of papers already exploring deep reinforcement learning. Even the scenarios are not very this standard, and that's why it's here the standard only, is very well defined, okay, which is a function of each block, okay, and what is the role of SDN in this. But for example, in network slicing there's a ton of different views. There is a view where an operator creates 3 slices and then puts services on those slices. So I create, for example, an enhanced mobile broadband slice, ultra reliable bandwidth low latency slice, and an IoT slice, and then I put services of more than one tenant using the same slice, because I built those 3 slices with those specific characteristics. But there's another view which is goes beyond this, and in that view I give a slice to each client, to each tenant, so I can have hundreds of slices running on my network, more complicated. So there are different points of view here. This is all, in the end, it's all still in the cutting edge of how this is evolving. In concrete terms, in terms of research, it already has some years, but in terms of implementations, this is very much in the beginning. Okay. So this is all we have. Next week we can have class if somebody appears to do some revisions. Okay, because next week would be the test, but it had to shift to Wednesday, so we get the class without. So this was planned to end today, but we have that extra class because instead of doing the test on Monday, we have to shift it to Wednesday.
O senhor está a pensar em usar algo que vai para resolver exercícios ou é só tirar dúvidas?
Posso fazer uma passagem pela matéria, que é o que às vezes fazemos. Até está um vídeo já de uma aula do ano passado que também tivemos tempo para fazer. Portanto, é o que for. Às vezes posso estar a fazer uns exemplos de que não são de lado nenhum. No BGP voltarmos a ver a história do Next Stop Self, dos PECs, não sei o quê, depois nos Service Providers, do que é que aprende o MAC do quê, como é que aquilo faz os mapeamentos, não sei o quê, e para fazer assim uma passagem rápida nas coisas mais importantes. Ou fazer uns exercícios, eu acho que também tenho um resolvido que vou lá pôr, mas esse depois acaba por estar lá no teste resolvido, portanto é um bocado de chover no molhado, mas normalmente é assim. Se vocês forem lá ver o vídeo, que está lá